Now we've used our auto booster to get a duty point for our pump. Let's look at replacing the auto booster with a pump component and modelling actual pump performance in the system. The first thing we can do is to change our auto component to a centrifugal pump component, which will allow us to model the performance of any pump within the database. Capacity, efficiency and MPSH curves can all be added to entries in the database. Have a look at the next video in the series to see this demonstrated in more detail. Now we have a pump component in the model, we can choose our selected pump from the database by clicking here. In this case, I'm going to select a Gould pump that I know should match this system. Now we have a pump model complete with the curve. We are no longer constrained by our inflow. The pump will deliver a flow based on the system curve and the capacity curve. So we can now reinstate a controller into this leg. To model this system as a complete circuit, let's include a reservoir tank here in place of this pressure node. A reservoir allows us to specify pressure and fluid just like a pressure boundary, but it can also accept multiple connections. Next, let's add some return headers to the tank. Let's multi-select them and set them to a 4-inch size. Now I can go into the list view and select my pressure boundaries and delete them all. This will provide a connection point for each leg to the header. Finally, let's add some heat exchangers to the circuit. Fluid Flow 3 has shell and tube and plate heat exchangers, and will calculate friction loss through each one using standard relationships or provided manufacturer's data, which essentially allows us to specify a loss coefficient for the exchanger. I'll leave the heat loss calculation off for the time being. We'll look at heat transfer options in a separate video. Now we can calculate the model and see how our pump performs. You can see a warning has appeared, so let's have a look and see what's going on. This valve is unable to control because insufficient flow is being delivered to the system by the pump. If we look at the pump results, we can see a total inflow of less than our minimum requirement of 50 meters cubed per hour. We can also check the pump chart to confirm. So we're left with some options. We can select another pump, or we could change the parameters of the currently selected pump. Fluid Flow 3 allows us to change the impeller and rotational speed of the pump and apply the affinity laws to generate a new curve. The maximum and minimum values specified here are defined in the database, and we recommend that these values remain within approximately 20% of the original curve data. The affinity laws tend to lose accuracy if we move too far away from the entered data. Let's speed the pump up to 1200 RPM and recalculate. You can see now that we are getting sufficient flow into the system and we are operating at a reasonable point on the curve. However, there is not much scope for getting additional flow out of this pump, so in this case perhaps selecting the next size in the range may be a more appropriate solution. In our next video in the series, we'll look at the databases available in Fluid Flow 3. Databases are a powerful feature and save a significant amount of time when modeling systems.